everyone, and welcome to the Data Idol Summer School, and welcome back to our community who have been following us for the last 5 years. Also, welcome to those of you who are new in our community and new to the Data Science Festival. So hi, I'm Charlotte, and I'm the Recruitment Operations Manager at Data Idols. The Summer School is a new pilot programme in partnership with the Data Science Festival. It will run live for 3 months, so you can learn in real time and pick up new skills from the comfort of your own home. These sessions are designed at an introductory level, ideal for any of you who are transitioning into data or any of you who are looking to start out in your career as well. Please use the Slack channel if you are watching this session live to chat with other attendees. The link will be in the chat soon. You can also use the channel Data Idol Summer School for any event-related questions, comments, or feedback. I'd also like to thank all of our partners who have made this event a success and for the 400+ hours it's taken our team to make this summer school a reality. All sessions have been pre-recorded and can be watched back at a later date starting from September. So from September the 1st, you will be sent a link to watch all the sessions back. They'll be free to watch at any time, so if you miss anything or want to learn at your own pace, then they will be available for you. Today, we will hear from Elliot and Rohit from Cleo. They will be giving a session on how to train and deploy models into production. So thank you very much for supporting the Data Science Festival in partnership with Data Idols, and we really hope that you enjoy the session.
Hi, I'm Elliot. I'm going to be presenting today on a few bits and bobs around how you might deploy and maintain your models in production and kind of maintain and iterate on them. I kind of worked on this with Rohit, but I'm just going to be doing the talking, but just wanted to give some credit there. Yeah, so a bit about me. So I'm a data scientist at Cleo. So Cleo is kind of a financial management app. So for things like budgeting and helping people save and generally kind of improve their financial health. And it's quite a kind of AI-driven company. So there's a lot of models that we're putting into production and using to do things like forecasting balances, kind of fitting people's incomes, and various different models that we have in production. So it's important for us to be able to maintain those models and kind of iterate on them and improve them while kind of keeping things straight in our heads. So I'm kind of going to talk through an overview of how we could arrange a pipeline to do this kind of thing. So the general structure that I'm going to talk about today is that say you have a model, you have a prototype, and maybe you've got it into production somehow. What are the problems that at that point, after you've designed your model, you've trained it, you've evaluated it, at that point, what problems are you going to encounter? Then I'll kind of outline a sort of conceptual structure of how you might have a deployment pipeline to let you automate training your model and getting it into a production service. And then a deep dive into an example of a particular sort of instance of this conceptual structure, kind of pretty similar to what we're using at Cleo. And then finally, I'll kind of return to this first section around the problems that you'd encounter after shipping your model and how this particular structure will help you solve these different problems. Okay. So as I say, I'm kind of going to be skipping in some ways the interesting part of machine learning. So the data fetching and the model training and the iterating and the designing. So we're going to assume that we have some kind of supervised learning problem, and you've got your data, you've trained your model, your metrics look good. That stuff is all sorted. I'm going to be focusing on the next steps. So let's imagine that you have your model, and what you want to do with that model is you want to make some real-time predictions. Maybe you have some application, maybe you're working on an app that you need to get some result, like maybe this is a user's historical balance. What do I think the balance is going to be in n days time, something like this. And you want to in real time be able to get the sort of state of a user and send it to some model and get an idea of this forecast. So the most common way that you would sort of productionize this model is that you create a service, like an HTTP service. So we're going to send a request containing like the feature vector, the various features about that user, and we're going to get a response back, maybe some JSON containing the prediction, essentially the output of the model. So what do we want from this service? We want the service to be reliable. So at this point, we're past the point where we are just iterating slowly on, okay, we've got some predictions. Oh, I messed up. I've got an error at prediction time. We're really using this in production to make actual decisions that customers will see. So we don't want to every 10th request get an error, because that's gonna harm the business or whatever application you have. So we don't want to so we want it to be up. We want it to be available. We want the service to be scalable. So if we have maybe 10 times more users or whatever we're predicting on, we don't want our costs to shoot up massively or just not be able to scale the service at all, maybe to get really slow. We kind of want to avoid things like this. We want it to be sort of linear in the demand at worst. If we do make some change to our model or to our kind of model serving logic, then we want to, and if indeed it goes wrong, if we start to send back strange predictions, then we want to be able to pretty quickly go back to the previous version. And we want that to be quick and especially easy to do, because maybe we'd be in a stressful circumstance where we'd want to do that. Another thing we want to do is that we want to be able to quickly and easily iterate on a model. So we want to be able to suggest some change, understand if it's better, and if it is better, kind of get it into production quickly so that we can maybe try our next idea. We want that kind of loop to be pretty fast. And finally, we want to be able to easily experiment with our model. So maybe we have two candidates and we're not quite sure. There's some trade-off there of maybe this version of the model looks better in some ways, but this other version looks better in other ways. And maybe we want to run them side by side and do some randomization to get an idea of which is better. So as I mentioned, this is after the first release. So maybe you have your model, and maybe even you've kind of hackily cobbled together some service exposing this model. Down the line, what problems are you going to encounter that you're going to need to solve? So the first thing that you're going to want, probably before your first release, but at least soon after, is you're going to want to understand how to monitor how this kind of model service is doing. So I've kind of split this into two classes of monitoring. The first is the sort of boring monitoring, by which what I really mean is things that are pretty general to any sort of software engineering service. So that, and not specific to kind of machine learning or data science. So that would be things like, is my service up? If I send any sort of request, is it even reaching my service? If I ask for a prediction, is something at least happening? Is the service running on the host or IP that I'm sending my request to? Is my service returning a bunch of errors? So if indeed I can kind of talk to my service, is it returning something sensible, or is it just returning maybe something gone wrong internally and am I returning a bunch of errors? I'd want to know about that pretty quickly. How fast is my service responding? So not only the sort of latency, so essentially the latency of the service. So that would include the things that are outside of the actual model prediction, if there's any data fetching or going on internally, but also indeed the time to generate a prediction from this model. Maybe we have some worst case scenario where we don't want to go above it. If it's going to take more than 150 milliseconds to generate our prediction, then that's going to impact the user experience or whatever your application is. So we'd want to know about that. And finally, what resources are my service using? So am I going to run into problems with scalability if I just have this one instance generating my predictions? If I'm kind of reaching close to those ceilings of running out of memory or saturating the processor, then then there's problems. And maybe in the other case, maybe we're massively over provisioning the service and it's got way more resources than it needs, and we can maybe save some money. So that's sort of the sort of things that you'd want to monitor from a kind of boring perspective. And on the interesting side, so this would be more like the kind of machine learning concepts. For the requests that I'm sending to my service, are the sort of features that I'm sending looking broadly like what I've trained on? Maybe if we've got some mismatch between the data that we trained on and the environment in which we're generating predictions, that might be something that we'd want to monitor to check that the drift isn't too big, because we might want to retrain the model, or maybe there's some problems about how it's deployed that we'd want to see there. Kind of similarly on the prediction side, let's look at the different predictions that we're generating, maybe this sort of forecast balance in n days. Again, if the predictions that we generate look very different to what we trained on, then maybe that's, or I guess in our test set, then that might be something that we'd want to look out for, that might, again, signal that something's going wrong in the model or the way it's being called. And yeah, in general, maybe in terms of latency or any other characteristics of the model, is it looking like what it looked like in my prototype stage? Has there been any kind of gap where something's gone wrong between that prototyping and into production? So that's one thing that you'd want to solve. Another thing that you might come across is maybe you have this service, this model running in production for 2 months, and it's doing fine. There's no particular change in its performance, but in that time you've kind of gathered a bunch more data, a bunch more kind of training samples, and you think, well, maybe we can do better. Let's keep the same architecture, not make any sort of logical changes, but just we've got more data, just shove it into the model. Let's see how it goes. So maybe you have this sort of notebook, and you have this sort of collection of scripts that you use to get the model into production. And then maybe at this point you think, okay, where was that notebook? How do we train this? Okay, I've got this notebook here, but we made some changes and forgot to commit them. Maybe you have, it's hard to keep track of what happened last time if there's not much kind of systematizing of this process. Maybe you'd think, well, what data did we train on last time? So how much more data did we have? Well, we ran this 2 months ago. It would be good to know how much extra data we have, but oh, we didn't. We just used the training set immediately to train a model. We didn't persist it anywhere. So it's hard to compare the data we have now with the data we trained on in the original deploy. And has the new data, does it look similar to what we had last time? It's kind of hard to do that comparison. And then the deployment, maybe there's some ad hoc scripts that we have, and we have to kind of dig them out again and kind of run them in the right order. And there's some tribal knowledge that maybe we've lost about how to invoke these arbitrary scripts that we have scattered around. Maybe that's a problem. A bit similarly, so maybe you managed to get your service retrained, things look better, you deploy that, and then after another 2 months, someone comes along and they're like, well, we did train this model, but we didn't really do a proper job of kind of tuning the hyperparameters of the model architecture. Maybe we can just sort of explore the space a bit more, and maybe that we can get a better model just by tweaking these hyperparameters. So let's go do that. So we pick out this training notebook that we use, and we fetch the training data again, and we change our sort of model fitting logic to do some hyperparameter search. And indeed, we see on our evaluation metrics that, yes, this model is doing better. And then you think, well, is that because of the hyperparameter tuning, or we also now have a bigger data set than 2 months ago? Okay, so I suppose we can try and remove the old data set, or compare the current data set with the results non-hyperparameter tuned with the hyperparameter tuned, but it's not quite the comparison of the training data that was used for the last deploy, so that we have to make some assumptions there, and it generally becomes hard to understand what's exactly changed. Similarly, so maybe the service is running for another 2 months, and there's some whole new model architecture that comes along. Maybe we want to try out this new model architecture. So we dig out this training notebook, we change the model fitting logic to try this new architecture, we retrain it, and it looks better in some ways, kind of worse in others. Maybe on average it does better, but there's some subspace the subset of the feature space where it's performing quite badly, or maybe the performance characteristics are different. Maybe it takes a lot longer to generate a prediction, but that prediction is better. So we think, well, maybe let's just ship both and split the traffic. Some users get the current model, some users get the proposed model, and we'll just measure some metrics on the kind of user side and see which performs better and go with that one. So that's something that you might want to do. Another thing that you might want to do is maybe the service is run for another 2 months. You've made your decision on your A/B test, and we're like, okay, well, let's do another retrain. We've got more data again. You go through the process again. You sort of not paying too much attention. You just run everything. Yeah, it all looks good, and then you ship it, and you notice that from your monitoring, you notice that the new version's predictions look a bit strange. They're distributed a bit oddly compared to what you had before. And you kind of dig into it and you realize, something went wrong in my training data. It's got all nulls for every 100th user. It wasn't big enough to impact the evaluation metrics, but there's something funny going on. Okay, we need to just roll back to the previous model. This isn't working. Where is that model? You hope that it's stored somewhere. You didn't overwrite it when you ran your training process. You need to find the model, and then you need to orchestrate these deployment scripts to point to that old model, and maybe in this time there's some sort of business value that's being lost through the predictions of this kind of new clunky bad model. So at this point, maybe you would want some framework within which you can solve these problems, and it's a bit less ad hoc, a bit more structured. There's kind of well-defined ways to solve these problems outside of kind of ad hoc collections of scripts and notebooks. Maybe you want some predefined structure. So this is a structure that I'm going to go through in some detail about how you can split up these tasks into independent processes that should hopefully let you solve some of these problems. So what do we want from this pipeline? So this pipeline is a series of steps that's going to ultimately go from your raw data to having a model in production. So we want this pipeline to be flexible. So if we want to reuse this pipeline for maybe many different services, solving many different problems, we don't want to hard code in too many assumptions about how models are trained, how data is fetched. We want to kind of decouple them, decouple these steps so that we can flex each one to be appropriate to the particular use case. We want reproducibility. So this means that we want to not have the results of running a particular step depend on the particular version that's installed on someone's laptop who's running it. We want to be able to kind of safely rerun steps and know that it's going to give the same results. So this will put everyone on the same page and kind of make things a lot more consistent, make things a lot more predictable. We want auditability, so we want to know what happened. So in some of the previous examples, we want to know, have we changed our model fitting logic between now and 2 months ago? What's changed? Why have things changed? What's maybe the performance over time? We want to generally have a kind of central place where we can understand what's changed. We want scalability, so ideally we want these things to kind of scale linearly in the amount of data and the amount of users. We don't want things to become intractable quite quickly. Ideally, we want to be able to scale each of these steps sort of independently. So we don't have one monolithic process where for some of the time it's sitting around doing nothing, and some of the time there's big bottlenecks. And we also want resumability. So maybe if the data fetching step or the model fitting step take a very long time, then if something fails right at the end of the process, then we don't want to have to start all the way over from scratch. That will make the kind of iteration loop very long and make it just harder to make any changes. So we want to be able to, if we fail halfway through, resume from that point onwards. So one key thing that we would want from this pipeline is that we would want very well-defined kind of interfaces between the steps, which would essentially be kind of concrete artifacts. So we would have some step, and we would have inputs that would be essentially files or maybe a Docker image or a training data set. And we want these objects to be kind of immutable and not changing. So we wouldn't want, for example, just to keep the latest, say, model object or the latest image that we're going to use to serve our model. We'd want to give each a kind of unique identifier, and so that we can keep each version. It makes it very easy to, for example, roll back to previous versions, to compare to previous data sets. The point is that we don't want to mutate things after we've generated them. We just want a kind of bin of immutable objects so that we can be sure that things aren't kind of changing under our feet. So yeah, some examples of these artifacts that might result from running these steps might be a Docker image, or like a CSV stored in S3, or maybe some pickle of a model object, things like this. So here is a big diagram kind of explaining the conceptual pipeline that I'm going to talk through. So I'll go through each of these steps in detail, but just to kind of quickly run through from sort of roughly top left to bottom right. So the first thing we want to do, this BD step, will be to build the logic that's going to fetch the training data. So this isn't actually doing the data fetching, but it's kind of packaging up a particular version of our data fetching logic and emitting it as an artifact, that purple thing. So we have that as a kind of versioned tracked object. So the particular encoding might change, but the idea is that we have an object we can point to and say, this is our data fetching logic. Then we might run that data fetching logic. So that would, the effect would be to read data from some raw data source, some data warehouse or S3 or wherever, and make it available, do some processing maybe to get it into a clean state of, this is our training data. This is the set of samples that we're going to train on. Before we can fit the model, we would do something similar, like building the data fetch logic, but on the model fitting logic. So again, we want to be able to point to a concrete kind of artifact and say, this is the particular version of our model fitting logic that we want to run. So that would be going from our training data will be the input, and our model will be the output. And the model fit logic essentially describes that function, how we're going to go from our training data to our model. So that would describe the model architecture, any sampling, and it would also evaluate the model at the same time. Yes, so then we would run this model fitting logic, so this RF step in the center right. So that would act to read in the training data, so that would be an input to the step, this prepared training data from the previous step, and then write out a model, an artifact, some serialized representation of a particular model, features in, prediction out, that would go somewhere. And then on the deployment end, so again, we need to kind of build a particular instantiation of the logic that we're going to use to serve this model. So this will be more like the kind of software engineering side of things. So we're going to write a web server that's going to accept some requests containing the features, maybe decode it, the request, make a prediction using the model, and generate a response. So we need to package that up into a versioned object somehow. And then finally, we need to deploy this model service. So the input here would be, I have a particular model artifact. I have some particular logic that I'm going to use to serve my model. And then I'm going to generate some, at this point, this isn't really an artifact. I'm going to start some sort of web server that's going to act to take this model to map features into predictions as a service. So that's the overview. So you might ask why there's these independent steps for kind of building the logic. You might imagine that just fetching the latest version of the logic at the point at which you actually fetch the data or fit the model will be sufficient. What are the benefits of this explicit step where we kind of freeze the logic into a single object? So one reason is that it's a good point at which to validate the logic, kind of do very mundane things like linting or running tests, like unit tests on the logic. If you did this at the point at which you actually fetch the data or fit the model, then you would do it more rarely because those things are maybe quite expensive operations. Whereas this kind of packaging step, you can do very often, like you can do basically maybe on every time you push to a Git repository, you run this stuff, and you can run it very often and get fast feedback. Another benefit is that it forces you to version your logic. So you can say, rather than saying, when I ran the data, it's some whatever version happened to be there when I ran this fetching logic, you can point to a very particular artifact that you can kind of download and look at and say, this is exactly the logic that was used to fetch this data or to fit this model, or this is what's being used in production to serve the model. So that's the reason for having these independent steps. It makes it a lot easier to refer to the particular version that's used to do these operations. So zooming in a bit on the steps. So the first, I kind of went into a bit of detail on these, but so the building this data fetch logic. So this is pretty abstract at this point, but essentially the input will be some source code that describes in some way a process whose result is to fetch some data. So to take the kind of most mundane example, that might be literally a Python script, a single file that gets a database connection to some data warehouse and then runs a query and then takes the result and uploads it to S3 as a CSV file. The output, so this is, but at this point we're just talking about building that logic, and the output would just be a frozen representation of that logic. So that might be just a Docker image, so like a little virtual machine that kind of encodes a particular machine that can run that Python script. So you run that image and the effect will be to run that logic that I described to fetch the data and to upload it in S3. I'm going to jump to the model fitting logic because it's a pretty similar story. Your input is the logic that's going to go from your training data to your model. An example might be that you have some Python script that's going to read a big CSV, fit a model to that data and save it to disk as, say, a pickle file, some serialization of your model. And then the result of this building process is, again, just some frozen representation. So again, maybe it's a Docker image that when you run it, it expects some training data to be available and it will save locally a model object, and you can kind of do some orchestration around there to make use of that logic. So going back to the training data, so this step, the input would be two inputs. The input would be the particular version of the logic that you want to run, and a kind of implicit input is the version of your data as it is now. So it can only see the data that you have now, and so there'll be some dependency there. An example of the inputs here might be this Docker image I mentioned, and maybe you have your data on Redshift or Snowflake or something like this. And the output is again a kind of versioned, immutable version of your training data set, which might be a CSV and S3 as I described. Going back to the model fitting, so the process here would be, what are our inputs? So we have two inputs again. We have the particular version of our model fitting logic that we want to run, maybe some Docker image, and a particular version of the training data that we've run from the previous step. And the result would be, it would run this model fitting logic, it would extract out this model that was saved as a result, and maybe it would upload it to S3 to make it available for later steps. So the building the model serve logic, again, similar kind of story. You have some logic that's describing a web server. It's going to package it up into a particular version and make it available for later steps. So that again, probably would be maybe a Docker image. So you'd have maybe a Flask server describing getting a request, decoding it, making predictions, and the output would be a Docker image that when you run it, it runs that service. And finally, deploying the model service. So the inputs here would be, you have a model artifact that would be an input, maybe a path on S3, and you have a particular Docker image that you want to serve. And the result might be, this would depend on the nature of the process, but maybe you would, to make it quite simple, maybe you would have a persistent EC2 instance, like a cloud machine that's going to run this serving image on some host and it's going to kind of copy in that model to make it available, that it's going to use it to make predictions. So that's a sort of conceptual overview of this particular pipeline, the different bits from a conceptual level. So now I want to spend a bit of time going through a particular kind of instantiation, a particular implementation of this structure, using kind of concrete tools and talking through how you might actually implement this kind of thing. So here is pretty much the same diagram. It looks very similar, but basically the contents of the little blobs has changed to sort of particular implementation. So you can, so I'll go through these, so I won't go over everything now, but you can see how the shape stays the same, but the methodology that we use to implement each of these bits has kind of become a particular example. So one thing that might seem a bit unclear at this point is how we're going to coordinate these steps. This all sounds very well and good, but when do we need to run these things, and how do we kind of pair them together, like express dependencies between these steps? So these things could, in principle, just be a kind of selection of scripts that we have available, and we run them in a certain order on maybe someone's local machine. But better would be to use a kind of dedicated tool. So things like CI tools, so for like continuous integration or continuous deployment. So if you're not familiar, there's a few different versions of this service, but essentially you want to, what they provide is dedicated machines to do these kind of orchestration tasks, and they will trigger these tasks when certain events happen. So maybe when you push to your Git repository with some change on master, then you want to trigger some events. Maybe if you make a pull request, you want to run some tests on your code, you want to build some image, and you want to get some feedback about how things are looking. And maybe you want to also run something on a schedule, maybe for generating your training data, maybe that you don't, because the raw data is kind of implicitly changing beneath you. Even if nothing has visibly changed, you might want to run that on some regular schedule. Yeah, so a benefit of among many benefits of running things these ways rather than on local machines is that you have a lot more reproducibility. You can really guarantee that the thing that is running on in the same environment everywhere. You have a kind of central place where you can see the history of how runs have gone in the past. And if you have maybe someone joining some organization, then there's a lower barrier to entry. There isn't a lot of delicate installing of dependencies on their machine. They can kind of click some buttons and run steps like fetching data, fitting models, because those dependencies are offloaded to the kind of CI tools. So in the particular example here, we use GitHub Actions to orchestrate this, but it's that most of these tools are pretty similar. There isn't a huge amount of difference. So digging into the particular pipeline steps that I mentioned, but again with particular implementation details here. So let's look at this data fetching step. So how you might want to do this is, especially at the data fetching stage, maybe the example I gave of a single Python script wouldn't work very well in some cases. Maybe there's a lot of pre-processing that you might want to do. Maybe you fetch some data, and then there might be some feature elaboration steps of clustering, or maybe even fetching third-party data, or general kind of complex steps. It might take a while. There might be multiple dependencies. There might be an opportunity to parallelize different tasks. You go do this clustering, you go fetch this third-party data, and we can do them in parallel. So it would be good to be able to express that and to take advantage of that opportunity of parallelism. And even within this step, to get things like resumability, so that if something goes wrong while fetching the data, you don't have to start from scratch. So Metaflow is a tool that we use to orchestrate these sorts of tasks. So I've put a link there for people have the slides. But it essentially lets you do these things. So it lets you define a kind of graph of tasks, and it will run them in the right order independently. It has a lot of support for this kind of reproducibility, for having a consistent environment. And you can, a nice benefit is that you can run the same logic locally while you're prototyping, and then without really any change, run the same logic on on EC2 on cloud services without really changing your code at all. So it kind of scales very easily, but also lets you prototype. Another thing that they have for this kind of packaging task that we need to do is that you can render this Metaflow flow as using AWS step functions, which is basically everything I described as Metaflow, but on AWS. So you would have a particular object on step functions that when you run it, it will execute the flow that I just described. So this will be the kind of packaging step that I mentioned. So the result will be a step function, state machine is the thing that it's called. So on the right, there's a bunch of code. It's not too important, but this is a very minimal example of Metaflow flow, whose effect would simply be to run a query on Redshift to get some kind of trivial single feature, single label bit of data, and then run some query on a data warehouse and then upload that to S3, as I kind of mentioned in the example. So as I say, maybe you would have multiple steps here. You can see that there's a kind of step decorator that demarcates these different steps, and you can express dependencies so it will scale to more complex pipelines. But in the simple case, it scales down quite well, so it's quite short to specify. So and then I mentioned that just using the kind of Metaflow CLI, you can say step function create, and the effect of that will be to render this flow as the equivalent AWS step function state machine. And then at that point, you can refer to that object in downstream steps of the pipeline, and you have versioning, and you can say this particular version of this flow is what was run. So that's that part. The similar packaging step, but for the model fitting logic. I guess there's some flexibility here, but maybe not a huge amount. I think the pretty obvious way to implement this step would be to have some Python script, or maybe a Python package, but in general a collection of a collection of code. I guess doesn't have to be Python, but the effect would be to read in some training data and to output a model object. So that would be using Docker. For people who aren't familiar with Docker, it's essentially a way to manage an image, which is kind of a small virtual machine, and you can guarantee that the logic that's baked into that image to run that logic is completely unchanging. You have a kind of immutable version of that logic, and you can store these remotely in an image registry. So in this under a particular image. So in the same way that a Git repository stores a sort of log of the versions of the code, a Docker registry can store many versions of these images. And maybe one thing to make clear is that you can have data in and data out. So maybe you can run this container with the training data that you have mounted within the image, and you can expect it to write a file locally within the container and then pull that out. So that would be the way that you would communicate with this container. You would mount the training data that you've maybe uploaded to S3, and then at the end read out the model artifact that's been written as a result of running the container. So these Docker files are how you specify the form of this image, essentially what the virtual machine looks like. You run a bunch of operations on some kind of base image, like kind of base version of an operating system. So in this minimal example, maybe you would have some code that expresses the requirements, the Python requirements that you need to train your model. So you can see on line 4, you would copy over some requirements and then inside the image, install those requirements. And then you might copy over some single file in this case that would read in the training data and write out the result. And then that entry point, the line 10, will say, when you start this container, run that file. So going back to the data fetching, so at this point, because we've rendered these step functions, this Metaflow flow into particular step functions, to actually run this step, it's nothing more than using the Metaflow CLI to trigger the particular step function that corresponds to our flow. So you would run something like this command here, and it would trigger the latest step function that would act to read the data, as we saw, and upload it to S3. So one thing that we would want here is we would want that training data to be versioned by the particular Metaflow version so that we can refer back to it. So we wouldn't have a single place, we would keep for every run the training data for each version of the logic. So at this point, we kind of have our two inputs. The training data in S3 has been run from the previous step, and from the model fitting step, we have some encoding of the logic that we want to run. So in this case, again, a particular example of how you might do this model fitting step is using AWS SageMaker. So AWS SageMaker is more like a collection of tools that are available on AWS to help with these kind of machine learning operations. And one feature that it has is it provides a way to simplify training of models in a kind of scalable and without writing much code. So without going into the details, essentially we're making a kind of call to the AWS through the CLI or using some Python library to create a training job. And the inputs would be, I want you to use this Docker image to actually do the fitting. And I want you to provide this training data inside that image container. So it would do the kind of boring work of downloading the file from S3, starting the kind of Docker image as a container, mounting that training data inside the container, waiting for the container to finish, expecting that the container's logic has written out the resulting model, pulling that out, uploading that to S3. So this is all quite pedestrian stuff, so it automates that logic. It also provides functionality like hyperparameter tuning and things but that's the essential feature that it provides. So you can see the result of this step would be some serialized version of the model artifact that would live in S3, again, versioned and immutable. Nearly there. The next thing that we need to do is we need to freeze the version of the code that's going to serve our image. So again, from a kind of ML data science perspective, this is not a very interesting process. Maybe we have some Flask app or it really doesn't matter, any web server that obeys the contract of features in, prediction out. So we need to keep the version of the Docker image that we're going to actually run to do that. One way that you can get away with writing not much code and get a decent implementation of a server is that so the AWS SageMaker suite provides a Python package that implements that makes a lot of assumptions about how your server is going to look based on the way that it's going to be used for using SageMaker. So you can see on the right an example implementation. Probably in practice you wouldn't have such a simple implementation, but you can see that you essentially just have to implement the very small segments of maybe when the server starts, you need to read in your model artifact so that it's in memory. You need to decode the input request. Maybe you have some JSON coming in, you want it to be a NumPy array or a pandas data frame. You have this predict function that takes that decoded data and turns it into predictions. And then finally, you need to take those predictions, which again might be in a NumPy array, and serialize it into some format that can be returned in the response. So maybe you return some JSON with a list of predictions for each feature vector. So you really just have to implement the minimal parts that are kind of unique to your model, and the rest is kind of handled for you. But this is just a convenience. Really, any web server that obeys the same contract will do. And then the final step for this particular example would be to deploy your model as a service. So again, we can use SageMaker for this. So SageMaker has, there's actually maybe 3 operations involved in actually going from the inputs to the outputs, but they're not incredibly relevant. So what we would need to do is we would create a SageMaker model. This would express a particular pair of, we're going to serve using this image, and we're going to serve this particular model artifact version. And then we would create an endpoint config where we can specify the resources that we're going to use to serve this. So how many instances we might use, how many different machines, and how big are those machines, how much memory and CPU do they need, really just the sort of infrastructure side of things. and then we would create an endpoint with that endpoint config, and that endpoint is essentially a service. So then we can send our requests to that endpoint. They'll be decoded and predictions made and encoded as in the previous slide. And we can start calling that from production, and we'll get a few things along with that. SageMaker will do a bunch of stuff for us that aren't very interesting, again, like monitoring and metrics, and we get the service that we want. So that's what we in practice do to actually deploy our endpoint. So now that we have this particular implementation of the pipeline that I've talked through, I want to go through the previous section about how the various problems that you might have once your model has entered production the first time, and see how this pipeline will help you solve these problems. So we looked before at monitoring your model, understanding the so-called boring bits and the interesting bits. So looking at the kind of boring monitoring, so this is really where you can save a lot of effort. So using SageMaker to create these endpoints, you get a lot for free. So for example, maybe you want, so this is kind of hidden in the library that I use to implement the server, but in practice, one of the things that the service needs to implement is a kind of ping or a health check that will check that maybe the model is loaded okay and that the service is just up. So SageMaker will automatically kind of ping your service every 10 seconds or something, so that you can get some alerting. Even if requests aren't coming in, you can get some alerting ahead of time that your service is having problems. SageMaker will also monitor the delay between a request coming in and a response coming in, so that you can monitor the performance characteristics of your model in terms of the latency, and you can look at the different percentiles. So this is all in AWS CloudWatch, which is just the sort of logs service in AWS. You can look at the distribution of responses, the type of responses that your model is returning. So if you have some problem, maybe your model is returning an error because if nulls are given in the feature vector, your model isn't supporting that, and it's just throwing an error and something's going wrong, and maybe you need to fix something on the client side or add some extra logic inside the service. So we can see the number of kind of 200, some successes, and the number of 500s, like failures that are coming, and maybe have some alerting so that if we get a lot of 500s, then we know about it. And resource-wise, we can see very clearly the amount of CPU and memory usage that our service has. So again, we can monitor to see if we're getting close to saturation, where maybe we need to scale either the number of instances or the size of a given machine instance. And again, see if it's maybe over provisioned and we can afford to use some wee little machines or just have fewer. On the interesting monitoring side, so this will be the distribution of features, kind of monitoring for feature drift, and looking at the prediction distribution. So as far as I know, there's less inbuilt support for this sort of thing, and maybe it will be a bit more dependent on the particular model, what you'd want to monitor. But there is a data capture option that you can specify for an endpoint. So this would mean that all of the requests that come in to the endpoint are captured, and the corresponding responses. So essentially the feature vectors and the predictions would be dumped into S3 so that you can see with some lag, so this wouldn't be real time, the input features and the output predictions, and you can do various bits of analytics on that to see whether maybe univariate wise features are drifting over time. You're getting a lot more from a certain providers from a certain bank than you used to, or maybe you need to retrain your model and make some other changes. And so that would be kind of on you from the point of logging the requests and the responses to build some analysis from that S3 to make dashboards and alerting and things like that. So on the retraining side, so mentioned that maybe you'd want to not really change your model fitting logic, but just get more data and see how your model might perform. So what would you do here? Going back to the pipeline structure. So you'd run the fetch data step, to get an updated training data set. So that would just be a matter of triggering this Metaflow kind of step function state, and you would have a new fresh training data set stored in S3. Okay, that's great. Then I can run my model fitting step. So it will just use whatever's the latest model fitting logic, use whatever the latest image that's been pushed is. And the input would be, maybe the default would be to use the latest training data. But if you want to specify it explicitly, the training data input would be the location in S3 that was generated in step 1. So we're now using the latest model fitting logic, using the newly generated training data. So during that step, we would generate some metrics. Maybe you'd look at the AUC, the precision recall curves, things like this, to understand if your model is doing better. And you can that would be generated as a kind of side product, side artifact of this model fitting step. So you'll be able to inspect that and decide go, no go, is this worth shipping to production? If at that point all looks good, then you would run your deploy step. The input then would be the model artifact that you generated in step 2, and you would have your latest model serving image, and you would have your either new or updated endpoint using that new model. And all of this is audited. You can see what version of each bit of logic is used. You can see whether accidentally the model fitting logic has actually changed between there and now. So I'm not just changing the training data. You can see what versions were used at each step, and you're aware of that rather than having to use your own memory. But in the case where the model fitting logic has changed and you want to check that is independent, you can always explicitly input, I want to use this particular version of the image that was used in production, and you're holding that logic constant and just changing the training data. So you have that flexibility. So another problem to solve would be, in some sense, the dual case. So where maybe you don't really care about your training data being much changed, but you want to change the logic that you're using to fit your model. So in the previous example we talked about, maybe you want to do some hyperparameter search. So maybe you would start a new branch and you want to change this model fitting logic. You have some scripts that's going to, again, read in the training data, do something and spit out a model artifact. And you want to add some, maybe now you hyperparameter search over some space. And you want that to be part of the model fitting. So maybe you have some branch that has that new logic in automatically, because this building process is just done on push. Every time you change your code, you get a new image. You would have this new logic encoded and available. At this point, you can run the model fitting step, and rather than the input being the latest the latest model fitting image that reflects what's on master, what we want to be in production, we can pass in the image that was built on your branch. So maybe you have some ID referencing the model fitting logic on this branch, so on this non-production case. And the effect of that would be, and we can refer to the current production training set if we want to make sure that we've held that constant. So the effect of that would be that we would have some model artifact, again, representing for this particular branch. And we can look at the results of that compared to the results of the last production deployment. And any changes that we see, we can be sure are to do with our changes to our logic and not changes to our data. And then if all looks good, maybe we're happy with this, then we can run the deploy step. I suppose we would want to merge the changes first, and then we'd want to run the deploy step with all of that, with that model artifact, and we're all good. So if you wanted to A/B test your model, how would we do this in this environment? So in some ways, it's a similar story. So maybe we have some new model architecture that we want to try out, and we suspect that it's maybe better in some ways, worse in others. So we push to a branch to build this new image representing our new model fitting logic. And we run this model fitting step, and again, using the image on our particular branch as input, and the current production training set, holding that constant. And we can run the deploy step. So at this point, I guess something that I didn't really describe is that we would maybe want to parameterize where we want to deploy our service on. So maybe by default, when we deploy, we update the current endpoint, the thing that's being called from production. So we probably want to have a decent amount of tests that we run before we run that deploy step. But maybe optionally, we can deploy a service on a new endpoint, on a kind of proposed or V2 endpoint. And then at this point, we have a kind of current production version, and we have this kind of postulated V2 variant version that we want to test. So at this point, this would be up to the client to implement this A/B test. So maybe on the client that's calling this service for a particular use case, maybe we would randomize by user ID so that 50% of users see our production, our current version, and 50% see this new version. And then on the kind of client side, we can monitor maybe some business behavior, like how good an experience users are having under these two different models. So that's how we can implement it. That would be the most flexible, but it would rely on the randomization, the kind of A/B test component being done on the client side. And an alternative, which may work for at least some use cases, is that SageMaker actually provides this possibility to have a single kind of endpoint, a single service, using the same serving logic, but where there are multiple model artifacts being served. So you can serve the same model, different models, but using the same logic and on the same endpoint. And then internally, you can specify random splits so that 50% of requests will go to place A and 50% to place B. So this is maybe a bit less flexible. The randomization is internal to SageMaker, and maybe if you want more complicated randomization, like you want to stratify or you want to randomize on not just the request, then this might not work, but the option's there. And the nice thing about this is that the client doesn't need to so-called know about this experiment. So also, how would this work if we accidentally deployed something that we didn't like? So we ran a deploy step and something's looking funny. So maybe hopefully we can, maybe we changed our service to log some extra stuff just to understand what's doing better. It's just sort of printing out maybe the mean prediction for this particular request. And we made a typo, or so it throws an exception in some cases, and we're having problems. So if this happens, then we would rerun the deploy step. And again, we have the flexibility. Of course, we have the historical images for all the previous versions that we've been serving. So we know the last known good image representing the logic that's good, that doesn't have this logging stuff added. Run the deploy step with that input image specified, and we should be good. Maybe we have the case that we discussed where you've trained some new model. It kind of looked good on the metrics. Maybe you didn't look too closely, but it turns out there's some problem with the training data, and your model is doing badly. It's generating kind of rubbish predictions. So in this case, it's really the same story. Just the input that you're changing is different. So you have the model artifact that was the kind of last known good version, the one that maybe was based on not this training data, but the previously fetched training data. We're kind of happy that that's good. So we're going to run the deploy step, and we're going to point at that model artifact and maybe the latest serving image. I guess it might be possible that maybe you've made a big change all at once, and there's problems with the service, there's problems with the model, or maybe you're just not sure what's going on and you just want to kind of roll back everything. Really, you just do both. You just go to the last known good service image and do the last known good model object, and hopefully you're good at that point. Yeah, so that's so that was the kind of pipeline that I wanted to talk through, and I've kind of touched on a few tools and services that you might want to use to implement this pipeline, and I've tried to motivate why this potentially at first blush over complex, over separated, over abstracted pipeline for going from data to model in production is worthwhile, and how it kind of sets you up for success in a few different ways. So going back to the kind of conceptual overview of the pipeline, I've spent a lot of time discussing. So the particular implementation steps that I went through, I think work well for Cleo. But my point is that I think this structure is the main thing to bear in mind, of having this separation and having kind of immutable objects be the result of steps. You can imagine if you squish the different steps together, then you'll lose visibility. So maybe if you fetch the training data and fit the model in the same step, then it's very hard to understand. It's kind of on you to save the training data and to do a good job of that, and to check that you can train a model from that in the future. Whereas having these be independent steps, and that, say, training data being the interface between the fetching and the fitting, kind of forces you to be able to roll back to that point, having them be separated. Whereas if you do lots of these things at once, then there's nothing really to stop you losing this logging. It's more logging rather than an actual interface. So yeah, that's everything I had. I hope that's useful. And yeah, I think that's all good.